Hello dear viewers, I am François-Régis ORTHOUS-DAUNAY. I am a lecturer in the Institut de Planétologie et d'Astrophysique de Grenoble, and I'm going to explain how our experimental work have put some constraints on what we know about the irradiation in the solar system. And I have the opportunity to give this talk thanks to the award we received, my coworker and I, from the Geochemical Journal for the paper called Ultraviolet Photon Fingerprints on Quantic Large Organic Molecules. So I would like to thank them very much, and I'm encouraging you to go through the paper itself to get the references at least. And so the question behind this paper is how does a quite simple process, which is a photon absorption, can modify the organic matter before any of these compounds being parts of a biological cycle. Does the energy brought by the photons end up in potential form inside bonds? Does it trigger polymerization, increasing the complexity of the system? Or does it simply degrade the system and heat it and break bonds? For the astrochemistry, it's not a simple problem, because actually both of the processes are observed and reproduced accordingly in the laboratory. So for instance, in an attempt to simulate motion surface irradiation, some experiments led to destruction of simple molecule, and in some cases trigger other reactions, increasing the size of the molecule and the complexity of the system. Other experiments dealing with larger molecules show that small fragments can be extracted out of big molecules when simulating interstellar medium. And I cannot mention the huge literature on the production of complex mixtures out of small precursors by irradiation of ices. So many simulations of dust grain covered by frozen simple precursor manage to produce remote sensing detection features of very large molecule, accordingly with observation of dust and gas in protostellar environments. So on top of what is observed in space, we should add everything we know about the solar system and its history. And so the sketch here tries to summarize different stages of the solar system formation. So going from the starless medium to the debris disk and formed planet through the accretion disk, there is only one thing that is simple, is that the irradiation is always due to stars, and they are mainly producing Lyman alpha photons. And luckily, these photons can be reproduced quite well in the laboratory with UV lamps. Moreover, and I'm not showing even the size of the literature about this topic, observation of molecules in this environment tend to show that there is a complexification through time. Molecules seems to be bigger and bigger as the planet forms, and maybe in this complexification lies the fingerprint in the UV photon chemistry. Well, such complexity seems to be recorded in some meteorites that we call primitive, or pristine, or simply carbonaceous chondrites. In these rocks, we find both very small molecules and refractory molecules that are completely insoluble in whatever solvent you can imagine. So except for very unstable compounds, most of the space environment molecules can be found in these meteorites. And this is consistent with the idea that they accreted material from all over the disk, and that some molecule could have been inherited from the dark cloud itself. So these are the best targets to look at the fingerprint of, I would say, ubiquitous irradiation process. So can we find fingerprints of molecular evolution whatsoever in a complex mixture? Well, the answer is yes, but I will try to convince you. Well, it depends on the mixture itself. But when it has a very peculiar origin, some features can be easily labeled as synthesis process evidences. So this is the case in biology, for instance, with the odd and even pattern in intensity in the mass spectrometry of lipid-like material. So I'm showing example for ground meat, but it works with vegan food as well. So on the top side of the figures, you have the classical representation of the mass spectrum, that is to say the abundance versus the mass of the probed compound. On the bottom side, well, you have another representation that shows you networks, that is to say molecules that are identified with a given differences. Here I'm only showing CH2 networks. Okay, and in these series, the orange series here, the living organics have odd and even patterns. And this pattern is lost through diagenesis of the sediments. So if we assume that crude oils, coals, whatsoever is produced out of lipid-like material, dead and buried in the sediment, we can see that the most obvious pattern of the synthesis process is lost through degradation of the organics. So this allows to interpret the crude oils are not synthesized as they are found. Well, aside from cosmochemical and geochemical application, I would like to say one word about the technique and the data treatment we apply on high-resolution mass spectrometry. So on the top, you still have the classical representation of the spectra, and on the bottom, you have this counterpart in what we call the mass defect versus mass diagram. So the major point here is that you transform only the mass information into an artificial 2D space where redundant chemical differences make points align. Okay, so my favorite comparison is with time. So if you have the exact date at which each of your lunch started for the last 10 years, you don't want to plot them on a single line, but you want to compare the shift toward noon versus the number of the day. So you can appreciate if there is a drift in your lunchtime with time. Okay, so keep in mind that each point on the bottom plots is associated with one measured mass in the classical spectrum. Okay, and if you have incremental mass defect correlating with the incremental mass added to the measured molecule, well, it's directly due to the addition of an invariant molecule pattern. If you compute the histogram of all the alignment in the mass defect space, you can identify most frequent chemical patterns and start grouping them as point networks. With the diversity understood and measured, quantified, you can organize the sample by choosing a relevant pattern. So on the left, you have the mass defect data in the mass defect versus mass space, transformed like I've just shown. There are thousands of points. We group them in CH2 families. And on the right figure here, you can appreciate the drawing of one line network. There are hundreds of them actually. And so you can convert the raw spectrum into several subspectra, each one associated with one CH2 network. And when you do that and examine the intensity pattern as you would do to find synthesis process fingerprints, you find the following. Each extracted subspectrum, CH2 subspectrum, has a bell-shaped envelope. That's to say, if you explain the bell-shaped pattern, you explain most of the whole sample synthesis. And well, such a smooth mass distribution is likely to be due to a continuous process. And there are several models for polymerization, and the one that fits the best with our data is the Wesslau model. Okay, it's based on the really simple idea that there is a geometrical growth growing from many small monomers to large molecules by fusing intermediate oligomers. Formally, it takes two equations. One is stating that each time you have a reaction, you increase the mass by a given factor that I would call alpha or whatever. Another equation is the distribution of the reaction themselves. Okay, so basically the distribution of the reaction rate. So let's imagine you have a gas with a lot of collisions, and for each collision there is a probability, call it P, of reacting and probability 1 minus P of non-reacting. And when you mix the two, you end up with this ugly expression. I prefer to visualize it. And there is a simulation of 10 different CH2 networks. For the sake of clarity, the growth factor and the reaction probability are set to a given value. The only thing variable here is the number of collisions. Okay? And so the molecular growth propagates like a wave in the mass coordinates. So both peak mass and width of the distribution increase with time. And this reminds of the data shown before in meteorites. Well, this model being well parameterized, it's easy to adjust each subspectrum with the closed Wesslau function and plot the fitted parameters. If we do that on a Murchison extract, we end up with the right figure, showing some kind of correlation between the two parameters, alpha and NP. In gray would have been the path followed by the previous simulation with fixed growth factor and just the number of reaction increasing. And so the blue points are the snapshot of the intrinsic variability of the synthesis process. The small size of the error bars tends to prove that the model fits well with the data whatsoever. And so the spread is due to the natural variability in the efficiency of the process here. Okay, so this is what we know about Murchison extract. It is well polymerized, and there is no sign of something related to photolysis itself, nothing obvious. To test if the UV irradiation played a role in the polymerization, we tried to submit this actual sample to artificial photolysis. And this was possible because we managed to extract a lot of material, and so we obtained a kind of priceless paint we could apply on sapphire rings, for instance, and put them in sample holder. And in order to deliver the fair amount of UV photons on the Murchison extract, we diverted the PICACHU apparatus. So this device is made to irradiate ices condensed on cold window. And so instead of condensed ice, we put sapphire window with some Murchison extract deposited on it. You can see a photograph of it right here, and the scale bar is 1 millimeter. And for the irradiation experiment, we were using UV lamps to simulate the Lyman alpha photon flux of approximately 100,000 years settled in PDR in photon-dominated regions in typical solar nebula. And the measurements were of two types. One was the quadrupole mass spectrometry of the fragments just right out of the irradiating sample. And another measurement was the Orbitrap high-resolution mass spec before and after. So for the quadrupole mass spectrometry results, so we measured, as said, the fragments that were sputtered away from the sample during irradiation. And the graph here shows the 7 most intense masses and their molecular interpretation. So it is represented in a 7-array diagram, so it's like a ternary diagram modified so you can evaluate 7 dimensions. And so the closer to a pole, the richer in this compound you are. And so the data point progressions shows that most of the fragments that have been sputtered away from the sample can be explained as it was a mixture of methane, water, and H2. They're all labeled on the graph. So at the beginning of the experiment, mostly water and methane mixed together are produced by destruction of the sample. And further, the production of H2 rises to reach eventually a plateau. And this shows that very small fragments are produced during irradiation, and they all are extremely rich in hydrogen. And this is confirmed by the high-resolution mass spectrometry. So for the sake of clarity, I will be showing the difference between two spectra before and after irradiation. And in orange are the molecules that where the abundance decreasing thanks to destruction of the samples during irradiation. And in teal, molecules remain thanks to resilience toward photolysis. So what is obvious in this plot is that the size of the molecule seems to play a very little role, because orange and teal bars are more or less equally distributed along the mass coordinates. On contrary, if you look at the points in the mass defect versus mass diagram, the orange points are concentrated in a given area. That's to say, preferentially destructed molecules have a higher mass defect than the rest of the sample. And this can be interpreted as a higher hydrogen content in this molecule. And so this is equivalent to say that the less resilient molecules seems to be richer in H2. And this is also equivalent to say that a high number of rings and double bond, that is to say low content of H2 in the structure, prevent the molecule to lose fragments during photon irradiation. And so this is true as bulk information, but you can go through the scrutiny of Wesslau parameters, and it shows that there is a global shift in the mass distribution of CH2 networks toward lower polymerization stages. So you can see here the Wesslau parameters in orange measured after the irradiation are in average on the left side of the plot. And this is true if you identify each CH2 network and plot the shift in this Wesslau space. You see that except for 4 networks, they all have shifted to the left. So this means the bell shape is preserved, but everything behaves like irradiation is going back in time as the polymerization is concerned. And so here is a reconstruction and a visualization. If we plot a representative Wesslau function and apply to it an equivalent transformation of what has undergone the Murchison extract during the irradiation. Okay, and this shift of the distribution is the closest thing I could call the UV irradiation fingerprint on a complex natural sample. Okay, and that's not a very good news, because as the fingerprint of the irradiation saves the shape of the distribution, we cannot tell whether or not it played a role in the synthesis. So unlike the diagenesis, there is no loss of a typical pattern. But if we compare 2 samples, we can relate one to another if their location in the Wesslau diagram is consistent with an expected path of irradiation. And so this was the case for one lunar soil we had the chance to measure, which has a leftmost position in these plots compared to irradiated Murchison and pristine Murchison even more. So if the irradiation is a simple process, that is to say it's not going back and forth in this diagram, well, it can explain the molecular evolution of a sample compared to another. And so as a result here, the organics in some lunar soils look like they are an highly irradiated version of Murchison. And this is consistent with the idea that organics on the moon are exogenic, brought by meteorites and then exposed to the sun, basically. And so the structure is modified, and this is in good agreement with what we reproduced in this PICACHU experiment. So as a conclusion, I would like to briefly summarize what we have done. We took natural extraterrestrial material, we irradiated it, and we measured lost fragments and what's remaining. And we found that the global polymerization pattern is not that much affected by UV photons, but we did notice a loss of H2, basically, or H-rich fragment. And this implies that if the UV photons were responsible of the polymerization, then it was absolutely synchronous. Otherwise, it would have destroyed the molecule by depolymerizing them back to 0. And this implies as well that we can tell if we can produce one sample by irradiating another. Okay, so this found application for the moon, and we have good hope that this will be helpful to describe the photolytic history on the Ryukyu or maybe Bennu regolith organics, if we can get some sample. So if we are correct, and I'm going back to the sketch of the beginning, so if we are correct, the implication is that the main environment where the UV photons are efficient to modify the organics are airless bodies, such as asteroids, Moon, and Mercury, maybe. So this is my conclusion, and thank you for watching.